So, welcome to the continuation of the lecture on the application of the concepts learned on the aperture coupled and probe coupled and the waveguide coupled structures. The topic which we were on was the difference between the source free and the loaded resonance. So, as we were seeing last time that the first resonant dip in this figure was at 3.08 gigahertz contributed by the TE111 mode. We now understand what is the TE111 mode in terms of its modal indices, and the second resonance by the stub resonance. Now, we see that the first resonant dip is close to the source free resonant frequency of the TE111 mode. এটা কি আবার আরম্ভ করব? So, it is seen that the first resonance is close to the source free resonance of the TE111 mode. Now, what is the difference between 3.08 and 3.18? Why are they different? So, this resonance is known as the loaded resonance and this resonance is known as the source free resonance. To differentiate between the two, let us see that if I have the resonator like this, as we said, the resonant frequencies come by matching the electric and magnetic fields at this interface, which is the dielectric interface epsilon r epsilon naught, this is the radius a of the resonator. So, by matching the electromagnetic fields, the tangential electric and magnetic fields at this interface. So, that leads to the characteristic equation, and the roots of the characteristic equation correspond to the source free resonance. So, the source free resonances are nothing but the roots of the characteristic equation. The loaded resonance on the other hand is the resonance at which the analytical tool or the simulation engine gives me a zero crossing of the input reactance. So, this is R in X in. So, a zero crossing of the input reactance. So, let us see here with respect to the figure. So, this zero crossing of the input reactance near 3 gigahertz. Okay. So, this zero crossing and the normalized resistance, which is R in by Z0 close to 1. So, you see R in by Z0 is close to 1, that is the input resistance is close to 50 ohm and the input reactance is close to 0. What does that mean? Let us go to the figure again. So, if the input reactance, let us say, is close to 0 and the input resistance, so this is my input reactance X in and this is my input resistance R in. So, if my input resistance is close to 50, I will get a match. Okay. So, R in by R0 or R in by Z0 will be close to 1, okay, and X in will be close to 0. Okay. So, R in will be close to 50 ohm and X in will be 0. So, this corresponds to the loaded resonance. So, what is the loaded resonance? How is it physically different from the source free resonance? The loaded resonance takes into account the presence of the excitation source, in this case the presence of the slot. The source free resonance has nothing to do with the excitation, it has nothing to do with the excitation. Excitation does not matter, it has nothing to do with the excitation, while the loaded resonance is an accurate analysis of the circuit or the antenna structure. It takes into account the excitation and everything is taken into account to find the actual input impedance. So, Z in, which is equal to R in plus J X in. Okay. So, it evaluates Z in taking into account the presence of the excitation source, and that is called the loaded resonance. So, we see that the loaded resonance is as important, or I should say the source free resonance is as important as the loaded resonance, because the source free resonance gives me the information as to which mode is close to the S11 dip. So, the dip in S11 corresponding to the matching condition, which mode is principally contributing to that resonance. This information is provided by the source free resonance. That is why we search the source free resonances near a particular loaded resonance. So, let us go back to the presentation. So, you see now the first resonance dip, which is a loaded resonance, is a 3.08 gigahertz, and the source free resonance of the T111 mode is 3.18 gigahertz. So, it is contributed by the source free T111 mode. The second resonance dip is at 3.42 gigahertz, is the stub resonance. So, this is the stub resonance. Now, the calculated 10 dB bandwidth is 26.8% and the measured 10 dB bandwidth was 29.17%. The calculation was done using the full wave Green's function technique, as we said before, but we are not going to concern ourselves with that, but that is intimately dependent or as a direct result of the modal concepts which we learned for the waveguide structures. So, the Green's function technique relies heavily on, or it is an expression of or an extension of the modal concepts, or the concept behind the theory of the modes. Okay. So, essentially it is also called the scalar Green's function technique, which we used here, okay, and in which the fields are expressed as a summation over the modal indices, just like the fields of the rectangular waveguide or the fields of the cylindrical structure, which we consider that they are a summation over the modal indices. So, just like that we have considered the summation over the modal indices, and we found the amplitude of the individual modes, and that is how we calculate the total field or the total Green's function, and that is the calculated 10 dB impedance bandwidth. The measured impedance bandwidth is 29.17, and particularly this antenna is easier to fabricate. Why do we say that it is easier to fabricate? Because of the presence of air, epsilon r 2 equal to 1 in the middle layer, because you see typically there is a problem in gluing two different dielectric layers. For example, epsilon r 1 equal to 9, had this been epsilon r 2 equal to, let us say, 7 or any other epsilon r 2 different from 9, then would have to glue this layer to this, and there might be, you know, like the mechanical problem of gluing, the problem of air gaps and things like that, which are avoided by choosing the middle layer dielectric constant to be 1. So, next, so we see the total bandwidth is about 30%, okay, using this kind of a structure. So, the next is we demonstrate the frequency tuning of this structure. Now, when we shift the frequency, we essentially excite a higher order mode, in this case the T112 mode. So, you see here that the third modal index P, which is 2, that is changed, resulting in a change of the resonant frequency without a change in the field distribution, because the field distribution are contributed by N and M, which is 1 and 1 here, which are unaffected, which are unaltered. Therefore, the field distribution of the T112 mode is exactly going to be the same as the T111 mode, which we discussed in the previous example. So, this is also the case of the centered slot with R2 equal to 18.5 millimeter, R3 as 23.5 millimeter, the length of the slot L as 12 millimeter, and the length of the stub 4.45 millimeter, and all the parameters are the same as in the previous case. And this shows that 2 the two resonance. The first resonance is the stub resonance and the second resonance is contributed by the TE112 mode. So, the first dip is at 4.02 gigahertz is a stub resonance and the second resonance at 4.88 gigahertz is close to the source free resonance of the TE112 mode, which has a source free resonance of 4.74 gigahertz, and as a result the calculated 10 dB impedance bandwidth is 30.18%, which is kind of the same as we obtained before. So, we demonstrate the frequency tuning of this antenna. Now, if we look at the center frequency of this, which is typically here, and compare with the center frequency of this, which is typically here, the previous example. So, we see that the center frequency for the return loss bandwidth in figure 2a, which is here, so which is this one, is at 4.44 gigahertz. So, you see this is at 4.44 gigahertz, close to 4.5, and which is displaced from the center frequency of 3.36 gigahertz in figure 1a. So, in figure 1a the center resonance frequency is 3.36 gigahertz and the displacement is by 32.14%. So, we shifted the resonance frequency without any effect on the radiation characteristics or the bandwidth. It is still the same broadband structure and we get the same radiation characteristics as we obtained before for the figure 1. Next, we investigate the case of a slot offset along slot length. So, here we see that we get 3 resonant dips. The first resonant dip is contributed by the TE201 and TE221 mode together. So, these are degenerate modes. So, they have the same resonance frequency. So, you see that the N and P, the first and the third modal index are the same for these two modes. So, they will have the same resonant frequencies because N and P are the same. However, the second index which is contributing to the field distribution is different. So, that means we have to investigate that how the field of TE201, how much it is different from TE221. If it is too much different, it is cause for concern. We should be aware of this fact because there is a presence of two degenerate modes having the same resonant frequencies, but having two different field distributions contributed by the difference in the second modal index. The same happens at the third resonant frequency, at the third dip of S11. We have the third dip which is contributed essentially by the third modal index. Here it is 1 here, here it is 2 here, and these two again are degenerate, TE202 and TE222, because N and P are the same here, and here also the field distribution is potentially different, E is different because the value of the second modal index is different. So, therefore, we have to see exactly how much the TE202 and how much the TE222, how much they are excited, to the extent they are excited, and whether they interfere with each other's pattern. Okay. So, we have to be concerned about that. So, you see how the knowledge of the modes enables us to focus on regions which might lead to the concept of, you know, like the polarization purity of the modes, that is the extent to which the radiation characteristics of one mode is affected by or may be affected by the presence of another degenerate mode. So, we need to be aware of this, okay, and the knowledge of the modes helps us to zero in on the regions of concern, okay, which we have little knowledge with using only the simulation tool. So, this is where the analysis comes in very handy and very useful. The middle resonance you see is the loaded slot resonance. Okay. The loaded slot resonance means it is the slot resonance affected by the presence of the DRA. So, in this case the y offset is given, YW as 4 millimeter with XW 0, with the the radius of the middle layer R2 as 16.5 millimeter, radius of the third layer, it is a 3 layer DRA, as the radius of the third layer is 22 millimeter, and the length of the slot 12 millimeter, and L stub is 7.75 millimeter, and all other parameters are the same as in the original figure 1. So, as we discussed, the first resonance dip at 4.56 gigahertz here, 4.56 gigahertz here, it is close to the source free resonant frequency of the T201 and T221 modes at 4.63 gigahertz. The second resonance dip at 5.54 gigahertz, which is here, is near the loaded slot resonance at 5.28 gigahertz. The third resonant dip in the return loss characteristics at 6.48 gigahertz, which is here, is close to the degenerate T202 and T222 mode resonances of the DRA at 6.26 gigahertz, and the measured 10 dB impedance bandwidth is 43.42%, which is larger than our case of the centered slot. So, we see that the case of the Y offset slot leads to a enhancement of a larger enhancement in bandwidth, but we have to be careful of these pattern characteristics which might be affected by the mode degeneracy at the first and third resonances. Then we do a slot offset along slot width, which is the slot offset along the x direction. So, here xw is 4 millimeter, the slot is offset along the x direction. So, you look at the original figure, the slot is offset along this direction, along the x direction. So, when we do that, we see that the first mode is excited is the TM101 mode, it is a TM mode, and that leads to the resonance at around 4.5 gigahertz, and the second resonance is contributed by the TE mode, it is a 112 mode, it is a broadside mode with a pattern which is maximum at theta equal to 0, and it is an end fire mode in which the pattern is null, we have a null at theta equal to 0, it is an end fire pattern. So, it radiates along the horizon. So, in this case the length of the slot is 10.5 millimeter, the length of the stub is 3.85 millimeter, and xw is 4 millimeter. So, we see that the first resonance dip at 4.44 gigahertz is caused due to the excitation of the TM101 mode with a source free resonance of 4.55 gigahertz. The second return loss dip at 4.92 gigahertz corresponds to the loaded resonance of the T112 mode with a corresponding source free resonance as 4.93 gigahertz, and the computed 10 dB impedance bandwidth is at 21.42%. But we have to be careful that this bandwidth which we obtain, there is a large big possibility that the radiation pattern is not going to be stable across this impedance bandwidth which we obtain, which we report at 21.52%, because on one side we have the TM101 mode with a monopole like or an end fire pattern, and on the other end of the bandwidth, close to the other end of the bandwidth, we have the T112 mode which has a broadside pattern. So, the pattern is likely to change from monopole like here to broadside there, and may consist of a mixture between the two in the bandwidth. So, therefore, the pattern characteristics will not be stable for the x offset slot. So, you see another important advantage or a deeper insight which we obtain for the wideband structure by using the antenna analysis from which we get the modes, and how the modes help us to understand that this bandwidth extension may be a cause of concern, because if we are interested just in bandwidth extension, that is fine, but if we are interested in radiation, in the radiation characteristics, in the antenna radiation performance, then we need to see that there might be and possibly would be a change in radiation characteristics because of the change in the modal type on the left side at closer to the lower resonance, and the right side which is closer to the higher resonant frequencies, because we have the end fire mode at one side and the monopole like mode on one side and the broadside mode on the other side. Okay. So, an X offset slot in that sense, if we are sensitive to the radiation characteristics, if it is for indoor applications, may not be a lot, we may not bother a lot, but in case we want a stable radiation characteristics, then we need to be very cautious about the X offset. Now, this is a dual band operation of the same DRA. So, in this case epsilon R1 equal to 14, the first layer 14 compared to the first layer permittivity 9 in figure 1. If you look at figure 1, it was 9, epsilon R1 was 9 here. So, here we change the epsilon R1 to be 14, the middle layer is 1, the third layer is at 7 permittivity, and the length of the slot is 15.2 mm and the length of the stub is 9.45 mm. So, we see that the other parameters are same as in figure 1. So, we see that the first resonance dip at 2.4 gigahertz is close to the source free resonance of the T111 mode at 2.52 gigahertz. So, here is the T111 mode contribution. Next, the second resonance dip at 2.76 gigahertz is the stub resonance. So, this part is the stub resonance, which leads to the merger between these two modes, leads to a wider bandwidth for the first band. So, this is the first band, and the second band which is here, if you look at that, the third resonance dip which is contributing to the second band. So, the merger between the first and the second resonance is contributing to the first band, the second band contributed by the third resonance at 4.08 gigahertz, it is close to the source free resonance frequency of the T112 mode at 3.95 gigahertz. Okay. So, the third resonance dip at 4.08 gigahertz is close to the source free resonance frequency of the T112 at 3.95 gigahertz. And the calculated 10 dB impedance bandwidth of the first and second band is at 26.74. This is due to the merger between the T111 mode and the stub resonance for the first band, and 9.28% for the impedance bandwidth for the second band, which is contributed by the T112 mode. Okay, so, here is the first band again and here is the second band. So, here is the radiation characteristics of the 3-layer hemispherical HDR is hemispherical DRA fed by a centered microstrip slot. So, you see the pattern characteristics are broadside, as we said, because we have excited the T111 mode. So, in both the XZ plane and the YZ plane with low cross pole. Here is the radiation pattern of the 3-layer DRA with the Y offset slot. So, when the slot is Y offset with respect to the XZ plane, the XZ plane is symmetric with respect to the structure. So, there is no effect on the XZ plane pattern characteristics, but because the YZ plane is asymmetric with respect to the slot, it is asymmetric with respect to the slot unlike the XZ plane. Okay. We have the pattern asymmetry or pattern distortion in the YZ plane. Okay. Because essentially my slot is offset along the Y direction. Next, we see the maximum bandwidth realization of the microstrip slot coupled 3-layer HDRA. So, here we have considered the centered slot XW 0 millimeter, YW 0 millimeter for the centered slot case, and we see for these configurations R1 12.5 millimeter, R2 17.5 millimeter, R3 22.5 millimeter, WS the width of the slot 1 millimeter, and the microstrip line substrate epsilon r is 2.2, the height of the microstrip substrate h 0.508 millimeter, and the width of the feed 1.58 millimeter. Okay. So, all other characteristics are similar to figure number 1, like epsilon r 1, that is 9 as in figure number 1. So, we see that we see the maximum bandwidth versus epsilon r 3 with epsilon r 2 as a parameter. So, we see that as epsilon r 3 increases, we get a optimum bandwidth at epsilon r 3 equal to 4, okay, and epsilon r 2 equal to 1. So, that is what we have chosen 9, 1, 4 as our optimized design here. You see in figure 1 we had chosen epsilon r 1 9, epsilon r 2 equal to 1, epsilon r 3 equal to 4. Okay. So, this is supported by the design curves, this is supported by the design curves for the maximum bandwidth realization. So, this characterizes the bandwidth versus the permittivity for the 3 layer HDRA. Let us stop here. We will next come to the probe coupled structure and the bandwidth realization using the probe coupled structures. Thank you.